Let's take a look at Newton's views on space, time, and motion. We're going to look at this article from the Stanford Encyclopedia of Philosophy. You can find that at plato.stanford.edu. It's basically a free resource with some really good, deep articles on various philosophical subjects, including philosophy of science. You'll find a lot of great information here about physics as well as philosophy. But let's get on with it and read the first paragraph.
Newton's views on space, time, and motion. Isaac Newton founded classical mechanics on the view that space is distinct from body and that time passes uniformly without regard to whether anything happens in the world. For this reason, he spoke of absolute space and absolute time, so as to distinguish these entities from the various ways by which we measure them, which he called relative spaces and relative times. From antiquity into the 18th century, contrary views which denied that space and time are real entities maintained that the world is necessarily a material plenum. Concerning space, they held that the idea of empty space is a conceptual impossibility. Space is nothing but an abstraction we use to compare different arrangements of the bodies constituting the plenum. Concerning time, they insisted, there can be no lapse of time without change occurring somewhere. Time is merely a measure of cycles of change within the world.
So it says Isaac Newton founded classical mechanics on the view that space is distinct from body and that time passes uniformly without regard to whether anything happens in the world. By space, I think we understand that Newton means three-dimensional space. It's distinct from body. So what does he mean by, what is body to Newton? Well, it really doesn't matter what it is to Newton. There's only two types of bodies, right? So, we've got the electrino, which has a magnitude of minus e over 6. And we've got the positrino, which has the magnitude of plus e over 6. And those are the only two discrete kind of bodies that exist in the universe. There's a certain spatial density of those. There's, a certain density of energy that they carry, but that's body. So, I think when Isaac Newton says space is distinct from body, I think that's very true. So I think he's correct. He just didn't, at the time, they didn't know what body was, but he was very pure in thought that they are distinct. Space is just a vessel. Point potentials are able to move around that space and the time, which we'll get to in a minute, based on the action that occurs to them. So I think we're very consistent with Newton in terms of this kind of a three-dimensional space. He goes on to say, and that time passes uniformly without regard to whether anything happens in the world. So, yeah, that's consistent. We're just saying time is linear, right? We're saying we've got one dimension of time. It's linear and it's forward moving. We're saying now is defined as synchronous, right? Throughout all space. So we've got space, it's Euclidean. We've got a body. Our body is these point potentials. And in terms of time, we've got one-dimensional time. It's linear. It's forward-moving. You could have a concept of now, which is synchronous and defined across the entire universe. For this reason, Newton, spoke of absolute space and absolute time, so as to distinguish these entities from the various ways by which we measure them, which he called relative spaces and relative times. So this is really fascinating, how this twists around itself in reality. So it's correct. I think it's perfect. I've adopted the same technology in the point potential theory of nature and the universe, which is absolute time and absolute space, right? They're just all orthogonal. We can model them with R4, and it's very, very simple. But the idea of distinguishing the entities from the various ways in which we measure them. See, this is where you get into this really perplexing concept in point potential theory, right? Which is, first off, you don't even have a measure of time and a measure of spatial distance just from the basic foundation of absolute space and time. They don't give you any metrics. They don't give you an origin. There's nothing, right? So it's just a vessel. These are all just vessels, in which to track the contents, which are going to be the unit point potentials. So, but just, absolute space and absolute time by themselves, pretty much empty. They don't really do anything. There seems to be some kind of recursion here. I don't know if it's like an ontological recursion. It's one of these things that kind of burns out my brainwaves. But first off, absolute space and absolute time, as I just mentioned, they don't have any metrics or dimensions. So it's only through these contents, which are the unit point potentials, that we could even begin to have some expression of units of time or units of distance, right? And if you think about it, the way unit point potentials work, right, like particles take action on each other that pushes them apart, and opposite particles take action on each other that pulls them together. And so you can imagine that, let's just say you took some random volume of point potentials that are flying around with different velocities. You just take a snapshot. You can measure the time. The time because it's a snapshot. That's fixed. And you can measure the XYZ coordinates of every point potential in that volume. And you measure the velocity of every point potential in that volume. And that's your information cube to work with. So then what happens? Well, I think you can realize that kind of the most primal assembly, the very basic assembly, instead of individual electrinos and positrinos, the point potentials, the most primal assembly would involve a pair of opposites, an electrino and a positrino, because they would orbit around each other like a binary, just like neutron stars orbit each other or black holes orbit each other. But in this case, it's like the masses would be the same, the charges would be the same, because they are both unit potentials, and they come in a certain charge that's constant throughout the universe. What I think is this fascinating recursion is that, and this was missed around 1900, is that as the binary takes on more and more energy, the dynamics, the geometry it works in this orbital motion causes the radius to decrease. And then as it takes more and more energy, the velocity of the point potentials in this binary is increasing. But when they looked at point potentials during the classical to quantum transition, there was some ontological confusion about the speed of light. Everybody at that time is observing the universe from the point of view of geometry 2. They don't realize there's a geometry 1, which is, entirely Euclidean and linear that we're talking about. They're sitting inside of geometry 2 and trying to figure out what's going on, but they're inside this curvy, stretchy space-time that Einstein described, right? They don't realize it, but all their observations are distorted by the fact that they're in this curvy, stretchy space-time, which is geometry 2, which is really held inside of geometry 1. Newton founded classical mechanics on the view that space is distinct from body. So let's just focus on that part. So we've got this thing called space, and we know that Newton was looking at a Euclidean space. Euclidean basically means three-dimensional, everything's linear. This is basically your x, y, z type coordinate system, describes a Euclidean space where everything linear, straightforward. There's nothing curvy and stretchy like Einstein. We're going to use the same thing in the potential universe. And the interesting thing about Euclidean space is, there's really no origin, there's no orientation, there's no signpost, there's no metrics, there's no definition of distance. Euclidean 3D space is a passive vessel. Now, you can put a coordinate system in there so you could virtually model what's going to be happening, and that's fine, but your coordinate system will be relative to the contents, which we're going to get to in a moment here. Newton says space is distinct from body. What does he mean by body? At the time, they were thinking, pretty large things. Newton was a long time ago, so I don't think they probably even knew about molecules yet, or maybe only a few. They certainly didn't know about atoms or electrons or quarks or the Standard Model yet. So by body, they're thinking of things at a much higher scale. Beyond the Standard Model, there was no thought for point potentials. Those are going to be the concepts that we use to create body. And what are point potentials? Well, they're really like a geometric point. I'm going to make a little tiny geometric point for the point potentials here. You can't see those yet. I'll fill them out in a minute. But the point is, it's really a geometric point that exists at some xyz in space. So these point potentials are going to have some xyz. Of course, we don't have an absolute reference frame, so x, y, and z are going to be something we choose. Often it'll be relative to the set of point potentials we're working with and their current positions or initial positions. So these point potentials are true geometric points. They don't have a physical radius in terms of size. They do exist. They do emit potential at a constant rate. For the purposes of being able to draw them, I'm not going to draw them as these little tiny points that imply true points. I will make them a little bigger so we can see, okay, here's the blue negative point potential, and here's the red positive point potential. And, those will just be our symbols that we use. And whenever we see those, we just know that what we're really talking about is a physical point in space, x, y, and z. Newton wants to talk about time passing uniformly without regard to whether anything happens in the world. So time in Newton's mind is a separate dimension. And the way we're going to deal with this in point potential theory is we're going to say, well, what is our scale of time? We don't know when it began, or when it's going to end. We know that there's forward progression of time, only forward. And we know that there's some point in time that we call now. And now is synchronous across the entirety of space. And so before now is the past, and after now is the future. We can predict the future. We don't necessarily know the future. But that's our scale of time. Again, we don't have any units of time. We don't have any measures of time. We kind of have an inherent view of now. And, as we deal with both of these, the space and the time of Newton, this Euclidean 3D space, linear one-dimensional time, we have to think in terms of a virtual observer. So a virtual observer is not a real thing. A virtual observer is going to be an entity that we can use for reasoning, and we can place the virtual observer anywhere in three-dimensional space and one-dimensional time. We can move our virtual observer up and down in scales in those in space and time. And we could, if we wanted to, have multiple virtual observers. The beautiful thing about the virtual observer in this framework is that everything's linear, everything's Euclidean, so there's nothing really complicated. You're just looking at different places in the universe, different orientations. You can turn around, you can zoom anywhere you want, and you can virtually observe, make logical, rational calculations about what's going to happen. The article goes on to say, for this reason, Newton spoke of absolute space and absolute time so as to distinguish these entities from the various ways by which we measure them, which he called relative spaces and relative times. And this is absolutely true. The virtual observer, which we just spoke about, is working in absolute space and absolute time. But in order to measure things, we're going to have to work in relative space and relative time relative to, our observer or relative to different point potentials in the universe. That's the only way we're going to be able to measure time and space is via this sense of relativity. Now, the good thing is in absolute space and absolute time, relativity is very straightforward. We just, the distance here, the distance there, we don't have anything, the time here, the time there. We don't have anything that is going to change those values in terms of like an Einstein type of thing where energy or mass could warp the space and time. That's just not going to happen in absolute space and time. So we can think of this geometry that Newton laid down as geometry 1. And the fascinating thing about the universe is it is a tale of two geometries. Einstein was right. There is a second geometry, and it does describe the way space-time describes. But Einstein was also wrong. There's a baseline geometry below his geometry, and that's this geometry we're talking about right here, absolute space and absolute time. Now, that's kind of confusing right now, but what you're going to see is that the point potentials emerge to form assemblies of point potentials, and one of the assemblies they form is essentially an ether of space-time. I know a lot of people have been told that the Michelson-Morley experiment in the 1870s disproved the ether. That's not true. There really is something, I don't know what you want to call it. You could call it an ether, you could call it a gas. I'm sure scientists will have some official name they eventually call it. But essentially, it's a construct of extremely high energy point potentials that is under such superposition, it's nearly non-interacting. So that makes geometry 2, which is Einstein's geometry, the squishy, curvy space-time. So this is a big idea, and it's really hard to reconcile your mind to it. The comforting thing is that below geometry 2, there is a Euclidean geometry of time and space. It's absolute, and everything's easy to think about. Now, the rest of this first paragraph is kind of talking about the contrary views at the time from Newton. And, they talk about things like views that denied space and time are real entities and maintained that the world is necessarily a material plenum. In a sense, that's right. I mean, in fact, the way we're going to find out that the universe works, space and time are virtual in a sense. You can't measure them directly. You can't see if they're really there. All we know is that we have point potentials moving around in a way that we can describe as three-dimensional space and one-dimensional time, that those point potentials are occupying that time and space medium. So in that sense, they are kind of virtual, they're imaginary. And it's true that you would never find like empty three-dimensional Euclidean space nearly always be populated with point potentials. Of course, in between point potentials, there's empty space, but that is at such tiny scales. You're not going to find a huge area of empty three-dimensional space. There's no such thing as a vacuum of that kind, like truly empty space vacuum. And so, a contrary view like this is actually a complementary view. So really, this is a healthy tension inside the ontology, trying to figure out what language you're going to use to describe time and space and how we actually think about them. Yet the contrary views do help us understand that we need to sort this out. And I think it is eminently sortable. Okay, concerning space, the contrarians held that the idea of empty space is a conceptual impossibility. We covered that. Space is nothing but an abstraction we use to compare different arrangements of bodies constituting the plenum. Yep, that's exactly what we just spoke about. Concerning time, they insisted there can be no lapse of time without change occurring somewhere. Time is merely a measure of cycles of change within the world. Yeah, this is another one where it's a very healthy tension inside the ontology. It is true that you couldn't measure time without seeing movement of point potentials, which are our body or our material, our entities inside the universe. So since time is going to be measured relative to point potentials, there can be no lapse of time without change occurring somewhere. That's true. Now, another thing we have to be careful about is when we're talking about space and time, we always have to be really clear. Are we talking geometry 1 or geometry 2? Now, the way I do that is I tend to talk about time and space as separate things. When I do that, that's going to be geometry 1, the Euclidean one. And if we talk about space-time, that's Einstein's geometry 2, which is the curvy, stretchy one. And it does get confusing, especially when we're talking about time. Like, are we talking about absolute time, or are we talking about time within geometry 2? Which is it? And so we're going to always have to be really careful. Otherwise, we can be creating more confusion or, being imprecise in describing how the point potential universe works.
Associated with these issues about the ontological status of space and time was the question of the nature of true motion. Newton defined the true motion of a body to be its motion through absolute space. Those who, before or shortly after Newton, rejected the reality of space did not necessarily deny that there is a fact of the matter as to the state of true motion of any given body. They thought rather that the concept of true motion could be analyzed in terms of the specifics of the relative motions or the causes thereof. The difficulty, or, as Newton alleged, the impossibility, of so doing constituted for Newton a strong argument for the existence of absolute space.
This paragraph is another great example of the tensions that arise as scientists or thinkers, philosophers are trying to understand the nature of nature, how nature actually works and operates from the lowest fundamental level that we can access. These questions that are being raised here are really at the crux of the matter, and considering that these thoughts were some 500 years ago, it's really quite impressive that people were at this level then. But let me just show you exactly the minimum information you need to be able to understand the universe at any given time. And that is, we're working in an absolute time and absolute space environment. And the only contents of time and space are point potentials. And point potentials can move. Point potentials emit potential that expands spherically, falling off with radius. So in a way, you can think of the universe as just little spikes of point potential that are emitting these circles. And that would be the entire universe. Go to the position called now in time. You don't have any information about where the point potentials will be in the future or the potential spheres that they will emit. This is another great paragraph that talks about some of the tension as the different scientists, philosophers, and thinkers tried to understand the basis of nature and how things worked. And the things that are being said here are not really inconsistent with the way nature works. They're kind of just different views, maybe from geometry 1, maybe from geometry 2, or just a different way of thinking about it. But let's kind of go through this a little bit. So let's say it says, Newton defined the true motion of a body to be its motion through absolute space. Of course, we want to add absolute time into that, right? We're going to keep track of the path of each body, which in our case is the point potential, through absolute time and space. So we'll give you in a moment what it means to keep track of the path. Then it says, those who before or shortly after Newton rejected the reality of space did not necessarily deny that there is a fact of the matter as to the state of true motion of any given body. So they believe that bodies have motion, but somehow they're rejecting the reality of space. That's interesting. I'm not sure what that means. They thought rather that the concept of true motion could be analyzed in terms of the specifics of the relative motions or of the causes thereof. Oh, I think I understand what they're saying. They're just saying since you're measuring and our metrics are all going to be relative to other point potentials, we don't necessarily need the concept of space, or that space isn't necessarily real if you just look at it from the point of calculating a geometry. Space is really just the coordinate system in a way. And that's an interesting way to think about it. So let's actually think about what's really going on. We do have a one-dimensional time, three-dimensional space. They're linear, orthogonal, Euclidean. And let's just consider the case of 2 point potentials moving throughout space. So over here we have time. We don't know what begins. There's now. And there's the future. We know that time moves forward. And then over here on the y-axis we have space. And we're just going to draw it as one dimension, even though you know it's 3D. That each dot will correspond to an x, a y, and a z. So if we have a point potential moving around space, let's say it's kind of on some path and it's curving, and then it gets to now. We don't know about its future path yet. All we know is the path that that point potential has taken on its history. And we'll assume we have saved all the XYZ points or some description of that path to incredibly high precision. And then we have another point potential that's also been following some path, and it comes to now. And so how would we describe those point potentials? For each one, we need the set of all points t, x, y, z. We need to know how fast it was going at each point along the path. So we need to know dx dt, dy dt, dz dt. So that gives us the velocities at each point, t, x, y, z. And the last thing we need to know is the charge. Is it positive or negative? And what do you think it's going to be for the other one? Well, it's the same thing. We need to know the set of all points. So let's make these sets. We need to make the set of all points t, x, y, z, dx dt, dy dt, dz dt, and the charge. And that's for the positive point potential. Of course, the positive point potential has the positive absolute magnitude, and the negative point potential has the negative magnitude. But if we have all that set of points, then we have all the information we need, and you can see that space is really only a vessel for these numbers. There's nothing else. If these were the only 2 point potentials in the universe, there's nothing else that we need to know. We need to know its entire path history, and that's it. Right? You've got 2 potentials, and for each one you have the set of all their entire path history. Now, why do you need to know the path history? Well, the path history tells you what potential was emitted where, and the magnitude of the emitted potential, because the velocity does factor in to the magnitude of the emission, because potential is emitted at a constant rate. If you're going faster, then there's going to be less potential emitted at each point. So that's it. That's all you need. And I think that gets to this paragraph that, as you think about it, well, is there really a space and a time, or are those just numbers that exist in some geometry that could be in some computer somewhere? And that's possible. I mean, if this is the entire basis of the mathematics for the universe, it could actually be a simulation. It's really weird to think of, and I don't think that's the way it works, but all this information is storable. I think if you consider the densities of the point potentials in the universe and the energies, that's impractical. So that's why I say I don't think we're in a simulation. But for a small-scale experiment, if we want to understand how things work, it's certainly eminently simulatable, and we'll be able to learn a lot about point potentials by doing those simulations.
In recent literature, Newton's theses regarding the ontology of space and time have come to be called substantivalism in contrast to relationism. It should be emphasized, though, that Newton did not regard space and time as genuine substances, as are paradigmatically bodies and minds, but rather as real entities with their own manner of existence as necessitated by God's existence, more specifically, his omnipresence and eternality.
This paragraph is fascinating. So we have this idea called substantivalism in contrast to relationism. As I mentioned, these are kind of two sides of the same coin in nature. You've got geometry 1 and you've got geometry 2. And certainly geometry 2 depends on geometry 1, but there's also emergence happening in geometry 2 that is very important so that we can understand things from geometry 1. Because if we didn't have geometry 2 and emergence, for example, the emergence of a measure of distance or the emergence of a measure of time, it would be very difficult to understand nature without those things from the perspective of geometry 1, which is the Euclidean space and linear time. So this is going to be a fascinating topic for philosophers in the academic fields to sort out, but these are some very initial thoughts on the topic. It says, it should be emphasized, though, that Newton did not regard space and time as genuine substances, as are paradigmatically bodies and minds, but rather as real entities with their own manner of existence as necessitated by God's existence, more specifically his omnipresence and eternality. Okay, how do you sort that? So we talked about this a little bit, whether space and time are genuine substances. They are vessels for point potentials and the emissions of point potentials. What does that really mean to be a vessel for those? Point potentials and point potential emissions, the sphere streams are flying around Euclidean time and space. But does that mean Euclidean time and space really have to exist? And it feels like they should exist, because otherwise how could point potentials move around inside of time and space? How could the emissions, the sphere streams emitted by point potentials expand forever through time and space if time and space didn't exist? And the one way to do that is if time and space are conceptual, and in some ways they are, or if we are truly in some kind of a simulation or an imagination. So they get to this idea of imagination when you talk about God and God's existence, right? So God would not be a material being, because if God were made out of point potentials, forming assemblies, then we would be able to identify where God is and how God takes action on the world. And scientifically, it seems very unlikely that we could find a point potential based God that is affecting the world the way religious people think of a God. In that sense, a God would have to be some being outside of the point potential system, outside of geometry 2, outside of our way of thinking about things. So if God is external to the system, and if we could conceive of our system as being a simulation, I suppose it could be God's simulation. So we would have the concept of God being the person or entity or operating the universe in a sense. But they would be outside of the system that we're in, outside of geometry 1, outside of geometry 2. And this does have some overlap with some key questions, right? So, we don't know where point potentials come from. We've said that they don't have a known origin. They don't have a known end. They seem to be immutable. You can't destroy them. You can't create them. So that begs the question of where did they come from? We don't know that. The same thing for time, in time and space. We don't know when time began. Did it have a beginning? Has it always been there? Has there always been time? What about space? Does space go on forever? Did space begin at some point? Does it have any bounds in any direction? Will space ever end? Three-dimensional space. These are really tough questions that we don't know the answers to, even in this new generation of the point charge ontology of nature. So that would be an area where people might want to ascribe things like that to a God, some creator that created these vessels, created the point charges and their physics and how they behave. So you could call that a God. Other people might, want to call that, sysadmin, for operator. It could be, an academic in some higher level space that's, simulating our universe because at some point it's become computationally inexpensive to actually simulate a very large set of point charges on the scale of our universe. I don't know. I personally don't think it's any of those. I think I'm comfortable with the idea that we just don't know where space and time started or will end, and we just assume that they've always been there, always will be, and I'm comfortable with that same thing for point charges. So in my view, I don't need a creator outside of this system to explain this system. And that's fine with me. Other people, may wish to explore these other alternatives. Certainly people of religion may wish to extend their religion into the concept of there being a godlike creator outside of our universe that creates all this stuff inside. Or people who are into simulation may want to seriously consider that, that we're running in a simulation, that there's a sysadmin or an operator or some academic driving that simulation. For me, I'm just going to assume that that's all not happening and that it's just the way it is. All right, here's some more detail from the article. First bullet, absolute true and mathematical time from its own nature passes equably without relation to anything external, and thus without reference to any change or way of measuring time. And that is true. Check, that makes absolute sense. It fits with the next area of point potential theory. 2. Absolute true and mathematical space remains similar and immovable without relation to anything external. The specific meaning of this will become clearer from the way it contrasts with Descartes' concepts of space. Relative spaces are measures of absolute space defined with reference to some system of bodies or another, and thus a relative space may and likely will be in motion. Yeah, this is basically true. Let's give it a little more detail and nuance. So if we're in space, and let's say we have a point charge in space, if our point charge is moving, if it has a velocity v, then at one point the point charge will be here, and then it moves at velocity v, and then now it's here, keeps kind of moving, right? What's happening to the emissions, right? So the first point charge made an emission, and then so T1 passes, and now the emission from point charge 1 has expanded. It's a potential sphere. Obviously, I'm showing it here in 2 dimensions. And let's say the velocity is constant. So we go on another increment of time, another t1. So this is now at this point. And then if we look back, when the point charge emitted sphere at t1, it's now expanded by this much, just like when now was here, the first one had expanded by this much. But now we're at this present now, and we look back and we see, oh, the sphere from t1 has expanded this much, but the sphere before that, one more t1, is now much larger. It's now expanded farther. So we're leaving behind this history of potential. It's like a sphere stream, because we're continuously emitting these spheres. They will, they are emitted and then they expand. And it's just like leaving behind, almost like a kid's soap bubble, as you take a soap bubble ring through the wind and a big bubble expands behind it. In a way, it's sort of similar to that, except it's very rigid and mathematical. It's expanding at a specific universally constant rate, the speed of potential, and it's continuous and so forth. How does that relate to our conception of space? And this is a good example of where the contents, the point potentials, and their behavior kind of tells us something about the geometry 1 of just the Euclidean space and time, which is that if we're going to define a velocity, right, we've got a velocity v, and that velocity has to be relative something. So if velocity is absolute velocity, then what is the velocity of 0, right? What is v equals 0? How would you know that you had velocity of 0? Well, this is beautiful, right? Because if velocity is 0, the point charge is just, t1, t2, t3. The time keeps passing, but the point charge doesn't move. And so if that's the case, then we can look at the potential coming off of it, right? So here's the first potential tracer that we plot. And then if we look a little bit back in time, the potential that was emitted there is now out here as a sphere. And if we look farther back in time, the potential that was emitted out here is a sphere. And so this particular sphere stream has a unique geometry, right? What can you say about this geometry? Well, the center of every sphere is the same, right? Which is the point of emission, because velocity is 0, so it's always being emitted from the same point. And it also is the case that the sphere stream has like a constant state while this is being emitted. This sphere stream goes from the relative t equals 0 of the point charge, and as it expands out, it's, of course, the potential is decreasing with 1 over r, right? So you're going to see this shape of potential, and if the velocity is 0, that shape will look constant. It will look like it's not changing. Whereas if you go back to this case, v greater than 0, you have this sphere stream that's kind of following the point, and as the point moves, that sphere stream will appear to have a shape that is different than the v equals 0 case. So that's a really important concept, and it again shows how this relative geometry ties back to the absolute geometry. And so in a way, geometry 1 is absolute, geometry 2 is relative, and what Einstein found is that in the relative geometry, there's very strange behaviors in terms of our measures of distance and time in geometry 2, right? And those happen in the relative space, and they happen because of point charges and the assemblies they generate, and we'll talk about that. The next thing says the place of a body is the space which it occupies, which is the location, and it may be absolute or relative according to whether the space is absolute or relative. Well, this is interesting. I mean, it turns out the location that a point potential occupies is a thing that ties geometry 1 and geometry 2 together. The t, x, y, and z, the location, is truly the same between the relative and the absolute. It's just we look at those inside of two different systems. Then it says absolute motion is the translation of a body from one absolute place to another, relative motion, the translation from one relative place to another. Yeah, that's all fine, check. So everything's a check. The place of a body is a space which it occupies and may be absolute or relative according to whether the space is absolute or relative. Yes, check. There is a linkage between where the point charge is and how we account for it. The point charge isn't in a different space in geometry 1 and geometry 2. It's actually in the same absolute physical location, which matches the relative location and is exactly the same point in both geometries. It's just the way we account for them mathematically in each geometry is different. And the way we calculate the distance between two items in each geometry is different. And the last paragraph here says, absolute motion is the translation of a body from one absolute place to another. Relative motion, the translation from one relative place to another. Yeah, check. Again, I really like how this is talking about two geometries. We're going to flesh that idea out even more in the point potential universe. All right, I don't know if we need to go through the rest of the article. I've given you the tools from the next era, the point potential era of science. But what I found when I read through the rest of this article is that I could take each point and resolve it to either geometry 1 or geometry 2 and understand how these two geometries are interlinked, and then figure out what these different philosophers and scientists were trying to say. And for the most part, I mean, I think the generic things they're saying make sense. You know, there's certain things they didn't know at that point in science, and so you see some anachronisms in there. So like if you take this paragraph 2.1 on the void, it says the most important question shaping the 17th century views on the nature of space-time and motion is whether or not a true void or true vacuum is possible, i.e. a place devoid of body of any sort. Ancient atomism, dating back at least to the pre-Socratic philosopher Democritus, held that not only is such possible, i.e. the void, but in fact actually exists among the interstices of the smallest indivisible parts of matter and extends without bound infinitely. Following Plato, Aristotle rejected the possibility of a void, claiming that by definition a void is nothing and what is nothing cannot exist. Okay, well, I mean, there really is a void. There's space, our three-dimensional geometry 1 space, which is Euclidean. It is in the interstices between our point potentials, and the void does hold the point potentials and the spheres of potential that are emitted and traveling through the void. It's a good question in our universe if you could have a volume of void or 3D space that held no point potentials and no point potential spheres. Certainly the volume in between point potentials doesn't have any point potentials, so in that sense it's a void, but it would have point potential spheres that have been emitted throughout time. So, you know, are you going to say that's not a void? You know, it kind of depends on how you parse that, how you define things precisely. So, you know, I just look at a lot of these things as easily reconcilable once you have the right ontology at the fundamental level, which I believe is this point potential architecture of nature. Anyway, you can go on. The article gets quite long, and you see it goes through the history of how people thought about this. First bullet here says time and space are real entities, even though they fit neither of the traditional categories of substance or accident. That's true. That time flows on eternally in the same calm and equal tenor, while the motion of all bodies is subject to acceleration, retardation, or suspension. Yeah? Time is distinct from any measure of it. True. Space is absolutely immovable and incorporeal. And that's true. So, you know, we talked about that a point potential with velocity of 0 has a different shape to its sphere stream than a point potential that has a velocity greater than 0. And that you could actually tell velocity of 0 from the shape of that sphere stream. Therefore, if velocity of 0 exists, the space in which it exists must be there and absolutely immovable. In other words, the point charges are moving around a space that is unchanging while they're moving in it. Gets into what Descartes had to say, some more Newton. And, I don't know. We don't need to go all through all these details. Like I said, I think you now have the tools to go through here, parse it, and understand what these philosophers were thinking about, why they thought about it. And you can see how to reconcile all the differences given the point potential.